Welcome. My name is Randy Atwood. I'm a past president of the Mississauga Centre of the Royal Astronomical Society of Canada. And I'd like to make a special welcome to all our guests here tonight for this special presentation. I'm going to do a little bit of an advert first, just tell you a little bit about who we are. The Mississauga Centre of the RASC, we're one of 30 centres across the country. The Royal Astronomical Society of Canada is a national organization of primarily amateur astronomers, which was started back in 1868. We've been here at the University of Toronto, Mississauga since 2003, and we became a center in 2006, so we're actually coming up to our 20th anniversary. If you're not a member and you'd like to consider becoming a member, it's very easy. We have a website, mississauga.rasc.ca. The annual membership fee is about $100. There are a lot of benefits of being a member. One of our major benefits is that we have a whole suite of telescopes of various sizes and shapes. And we have a telescope loaning program. So if you're thinking about buying a nice telescope, we probably have a nice one that you could borrow and check it out and see if it's something that you might want to go out and buy. We have our program here in this room. We have 2 meetings a month. Tonight we have a speaker night where we invite someone to come and give us a talk on various aspects of astronomy, space exploration, various things. And then the other meeting a month is what we call potpourri, but it's just a series of short talks by members on various aspects of observing and just whatever somebody wants to stand up and talk about. So it's quite a potpourri, I think, is appropriate for that night. The RASC, the membership at the various centers, they have very active public outreach programs, and we have an active program ourselves. We run monthly public observing nights at the Riverwood Conservancy, which is just up the Credit River, just at Burnenthorpe and the Credit River. We've had a long relationship with the Riverwood Conservancy, and we set up about a dozen telescopes there for about 250 people every month. And we can get it nice and dark, considerably dark anyway for the city. And we look at a whole bunch of stuff. So if you'd like to look at some different objects and telescopes or whatever, go check out the Riverwood Conservancy website. There's a small charge for doing that, but it's a lot of fun. So let me tell you about tonight. We have a very special speaker tonight, Ivan Semeniuk from the Globe and Mail. I want to introduce our speaker tonight. Theoretically, I've known Ivan for a long time. And I say theoretically because before I met him, I had interacted with him. And let me explain. I don't know when we met. Probably 90s sometime. Yeah. Late 80s, 90s. But I used to host a Cable 10 TV show. And the night of January 26th, 1986 was a Saturday. No, it was the 5th. It was a Saturday. And the only reason I know that is because it was 3 days before the Challenger accident. But it was also when we did a 2-hour live program because it was Voyager 2 at Uranus. And we had a live phone in. And my guests were Dr. Tom Bolton from the University of Toronto and Ian McGregor from the McLaughlin Planetarium. And I didn't know it, but years later, I realized that Ivan was had Tom Bolton as a prof. And so he called in and asked a question. So years later, he said, "Do you realize that I called into your TV show?" So anyway, that we go back. But also we've known Ivan during his days at the Ontario Science Centre. And I can't help but, with all the things that have been going on at the Science Centre, remember that the planetarium closed 30 years ago this year. And that's where the Toronto Centre was meeting. And at that time, Ivan was, I think, pretty quick to see if the Toronto Centre could then move up to the Science Centre. And we jumped at it at the time. So that's how we've been working together to promote astronomy education and aspects of the RASC. I think if you've read Ivan's work and if you've read his bio, you know that he's an excellent science writer for the Globe and Mail. He's written on all different types of really cool stuff. And being a science writer, you've got to have a really broad understanding of science. But he's also been very focused in on any activities that are going on in space and astronomy. And tonight he's going to bring his experience, his recent experience of covering all the different things that have been going on in space and astronomy. And I don't know, I think launching a large new telescope into space like Hubble or James Webb is sort of a double-edged sword for science writers because it just changes everything we are seeing out in the universe and maybe even get scientists arguing a little bit about what we're seeing. And he's had to interpret what the James Webb has been producing in the last few years. And I think that's going to be one aspect of his talk tonight. And I think he's even going to bring up a few interesting stories that have been in the news that might have sort of been, I don't know, sort of social media type stories or whatever. Anyway, he's got a lot to tell us, and we're looking forward to hearing our speaker tonight, Ivan Semeniuk of the Globe and Mail. Ivan?
Okay. It's wonderful to see you all here. Thank you so much for coming out tonight. Thanks for inviting me to come. Oh, what did I just... There. Oh, yes, thank you very much. Yeah, and then we just go up to slideshow. Oh, there you go. Perfect. Great. That's a fun memory that Randy brought up. So I was in Tom Bolton's class. For those who don't know, Tom Bolton famously, he was among those who identified the star around which the black hole Cygnus X1 orbits. And that was among the most famous pieces of science that was conducted at the David Dunlop Observatory, still Canada's largest telescope, still the largest telescope east of the Mississippi River. So that was something that happened in 1972. I was in Tom Bolton's class, so that was probably in early '86, with a couple of other students, and we thought it would be hilarious if we called our professor on while he was on TV, and he recognized us right away. Okay, I'm going to tell a Tom Bolton story that I rarely tell, but I wouldn't say that I was a stellar student in his class, but I think he sort of predicted my future as a journalist, because if you have been down, of course, if you know downtown at the U of T campus, the astronomy department is way up in the Burton Tower. Back then it was up on the 13th floor. And at one point I was in the elevator and he stepped in the elevator and it was just the two of us. And there's this kind of uncomfortable moment. And he looked at me for a minute and he said, "Semeniuk, eh?" He's like, "The questions you ask are like a grad student. Too bad about your marks." And then he left. And the door closed. Anyway, that told me that at least I could ask questions. So that was good. Anyway, nice to think of Tom now after all these years. And thank you again, Randy, for bringing me. I just already have felt very warmly welcomed. I'll say one other reminiscence, which is I have 3 children now, 3 daughters, and my youngest is 14. And I was just reflecting tonight that I was 14 when I went to my first RASC meeting in Windsor. And that was certainly a turning point in my life. And I'm sure I wouldn't be here tonight if that hadn't happened. So the RASC's always felt like home to me. So even though I don't always get out very much, it really feels like I'm in my hometown. So I appreciate that warm welcome. And it's been nice to see a lot familiar faces tonight. Okay, so let's get going. And in my usual style, I'm going to start with a total digression. Oh, I just did something. Oh, I see. That was a digression. That was more of a digression than I expected. Okay, thank you very much. Sorry about that. Wrong. You would think that the top button would advance things, but of course it's the right.
We didn't go over that. That's true.
Yes. Okay, so let's just talk for a minute about alien life. I'm sure many of you were aware of this story that popped up about a month or so ago, month and a half ago. The strongest hints yet of biological activity outside the solar system. That's the title of the press release that came from Cambridge University. Of course, Cambridge University, but seems very important. And it relates to the paper that you see here that was in Astrophysical Journal Letters, where a team claimed to have seen a possible biosignature in the spectrum of a planet orbiting around a star, a red dwarf star. Many of you here, I'm sure, are familiar with the concept of a biosignature. The idea is that there's some gas in the atmosphere of the planet that is somehow out of equilibrium or somehow shouldn't be there unless life was keeping it going. So for example, if you're looking at our planet from some distance and you could only analyze the light from Earth or the reflected light from Earth, you might notice that there's an oxygen atmosphere. Probably you'd see the ozone in the atmosphere. These are things that wouldn't be there unless you had plants on the Earth's surface generating all that oxygen. So, although there could be other potential explanations, but oxygen would be a potential biosignature if you're looking at Earth. So here, the biosignature had to do with dimethyl sulfide and then dimethyl disulfide, a couple of chemicals that are in our atmosphere in very small quantities, but they are associated here on Earth with plankton in the ocean. So the idea was that if this is turning up in the atmosphere of a planet that's, potentially because of its mass and size, potentially a planet that has a lot of water on it, then maybe there's some kind of marine ecosystem, and maybe there's also alien plankton that's kind of creating this stuff. So of course, predictably, it made a huge sensation. I don't know if you found it exciting. When things like this happen, for me, it's usually like something that you have to pay attention to, but already sort of in the first 5 seconds, this is probably not actually anything that we need to be talking about. But in any case, the headlines quickly came. I'll show you some headlines in a minute. Here's the actual data that was advertised. And the way this was promoted by the university, the lead author of the paper gave a news conference. What it was a public lecture. And that was live streamed around the world. And then lots of news sources just kind of quoted from that public lecture. So there wasn't a lot of perspective or context from other sources provided there. But here you can see what they're showing is a simplified graphic of the spectrum of the planet. And you can see how big the error bars are there. And if you find this not like a super convincing signal, you would not be alone in that summation. But this is a transmission spectroscopy. So what you're seeing here is, when the telescope, in this case the James Webb Space Telescope, looks at the star around which the planet is orbiting, it's seeing the light of the star, but it's also seeing the light from the planet. And the planet is giving off infrared, and JWST is sensitive to infrared light, which is one reason why it's out in space and very far away from Earth. So it can actually pick up that super sensitive, it can pick up that super low energy dim infrared light. So when the planet goes behind the star, you no longer see it. So then you only have the light of the star by itself, or the spectrum of the star by itself. And then when the planet comes out, you have both. So you can subtract one from the other, and what you're left with is, well, what is the light of the planet by itself? You can't see the planet individually, but you know it's there. because it's orbiting around the star and occasionally blocking the star's light. So when you do that, then you get that spectrum, and the contention was that there was this trace signature of dimethyl sulfide and dimethyl disulfide, which we probably aren't going to have to talk about very much after this. Anyway, here's some of the coverage. The coverage was very widespread. Here's BBC's Palab Goetz. Here's Carl Zimmer, the New York Times, both veteran, experienced, respected science reporters going all in. I mean, both of these stories have some caveats, but they are definitely, and they are also saying, they are not saying that life has been detected, but they are definitely at least taking the line that someone is saying that life maybe has been detected. So this generated a lot of interest. I was working on something else that day. So the first day, the Globe and Mail ran a story from The Wires, from Associated Press. And then I thought, well, we better take a closer look. And I had a chance to sort of kind of disentangle everything that had been said. And a couple days later, we put our story up to say, you know, this probably is not what it looks like, but here's what different people are saying about it. It's an interesting case because this is a case where science can get overhyped, or a result can get overhyped. People may say, where's the harm? It doesn't really matter. And sometimes you see this happen in the news media. I mean, it's one thing. Things get hyped up on social media. We expect that. We expect things to go crazy on the internet. But we're talking about, you know, reputable news organizations here. And I'm not saying that anyone's done anything wrong, but there's definitely a sense of excitement, and the media kind of have to respond to that. The tricky part is that one does wonder about the impact. I mean, I think that this is the kind of thing where astronomy engenders a lot of wonder and excitement and curiosity. Editors and producers are aware of that. So there's a willingness to kind of go big or be exuberant on stories like this, even though they often turn out to not really hold much water, no pun intended, with this kind of thing. And you might say, well, the stakes are low. This is not like a vaccine result or a cure for cancer or something else that might have immediate impact on health and well-being. So where's the harm if we go a little bit overboard about aliens and it turns out there are no aliens? Well, it's a good question. I find myself in the era that we're living in now with huge amounts of distrust in science that maybe these things are not as harmless as they seem. And I think that lots of scientists would have said that this should have been done much more carefully. But the thing is, some scientists are more willing to go out on a limb than others. You know, there's a spectrum of personalities in research, as there is in any profession. Some scientists are willing to say, you know, kind of go as far out there as the data will allow. Others want to hold back, and then the media have to sort of respond accordingly. So I'm not saying right or wrong. I'm just saying this kind of thing always makes me wonder about if there is a longer term harm. So my story talks about why people think that this was not exactly that this result is not to be believed. That wasn't the headline that I wanted. So scientists find strongest evidence yet of possible life. And then a couple days later, did scientists actually find the strongest evidence? I'm going to say that up till now, when there has been zero evidence, any amount of claimed evidence becomes the strongest evidence. That is a fact. That's what we're talking about here. My preferred headline was this. I guess maybe too much, too clever. That's how I would have. Because I actually think that this was an important story, but not because of aliens being discovered. I think it's a reminder of where we're at. And I think we're at a really interesting place. Oh, by the way, this was today. So the New York Times, so I have not written further about this. There are other things to do. But Carl Zimmer came back today. He collected 3 different papers, all of which trashed the original result. So if you're looking at the New York Times today, you can see more of that. So, you know, that's sort of the churn, the cycle. So, but here's what I think is interesting. If I were to sum it up, if I were writing a story today, I would include this sentence. People who've been following James Webb know that we're already at this. You know, I'm sure some of you have seen Sarah Seeger speak, or other exoplanet researchers who've talked about this for a while now. What we're talking about is something that is possible. I mean, 20 years ago, it would not, like a biosignature story would not have been plausible at all. The fact that the world was paying attention kind of signals that, well, this might happen at some point. In fact, maybe there's a high probability that it's going to happen in the near future. So it's no longer a question of whether we can find signs of alien life, but whether signs of alien life are there to be found. We don't know if there are planets that host alien microbial ecosystems nearby that the James Webb can access and measure the atmosphere and see a biosignature. We don't know if those planets are there, but if they are, the tools are in hand to see that. So this kind of signals, you know, just a reminder to everyone that we are on that threshold. Maybe the next time it won't just immediately disappear. Like in this case, the aliens disappeared not because Webb saw something or didn't see something. It's much simpler than that. I mean, when the original story was published, it's like, oh, it might take years before scientists can confirm this. And right away, people were saying to me, it is not going to take years. You just have to look at how they reduce their data. We don't agree with it. No one would do that. So, you know, it's just sort of, it came down to an interpretation of data, not the reality of the signal. But the next one might be different. There might be a signal, and it might be the case where the research community agrees there's a signal, but there will be lots of disagreement about what the signal means. And then we'll kind of be living with that question mark for years and years. We're not living with this question mark. So you don't have to worry about dimethyl disulfide for now. But it'll be interesting to see how long before we get the next one. The thing that makes this interesting, it's the first biosignature claimed with James Webb, and it's a false alarm, but I'm sure more will be coming. So, and this sort of speaks to what happens when journalists like me and others, colleagues at the Globe and Mail and other media outlets, have to contend with scientific research and how to talk about scientific research. Because, you know, there may be scientists I'm sure there's some scientists in the audience tonight, or many of you are familiar with how science works. And it can be very incremental. It can be very uncertain. Uncertainty is a big, huge, important aspect of how science works, and dealing with uncertainties and trying to draw inferences from what available data there are. And translating that into news is tricky, because news is concerned with facts, what's real, what's not real. I mean, that's the whole point. Let's get to the bottom of things. And it's hard to get to the bottom of things when the whole, you know, when uncertainty is part of, is baked in. So, and it's interesting because among the most important, I'm going to say, you know, hopefully you'll find this when you read stories by Globe and Mail reporters or other high quality journalistic outlets, which I encourage you to support with your subscriptions, because otherwise no one will do this. When you're reading about a result, don't just look and see what the author of a study or the discoverer says, but does the news story also include voices who are not part of the study, who are not part of the discovery, and what do they say? And a key, you know, I do lots of stories that involve studies or published research, and usually when I'm picking up a study and deciding if it's something I want to cover, my first question is not, okay, can I get the scientist on the phone? I know I can get the scientist on the phone because they just put a paper out. Of course they want to talk. I want to find out who can I talk to who has not involved with this research, but knows enough about it to comment as an expert. That's a person who has nothing to gain by talking to me. It's literally a total waste of their time. But out of the goodness of their heart, they will talk to me and say, okay, well, this is what I think about this paper. And typically, it's someone who's familiar with the work and familiar about where that particular research group fits into the larger ecosystem of that field. And you talk to a few of those people and you kind of get a sense of, okay, how does the whole field respond to this? That doesn't mean they're right or wrong. It doesn't mean that a discovery isn't a discovery, but it helps to put things in perspective and sort things out. So for example, when sometimes I teach science journalism, and when I do that, I try to prepare students who are learning how to do this kind of reporting. What happens when you call and talk to a scientist about another scientist's work? And usually I say there are three possible answers, or there's lots of possible answers, but they usually fall into three categories. So here are the three ways that scientists talk about other scientists' work. One way, like you might say, what did you think about this paper? What did you think about this study? What did you think about their findings? So one possible answer is this category. Everybody knows that. So a lot of the stuff that you see published, promoted, universities, journals are putting out papers. For the first time ever, scientists have found this, discovered this. You talk to people in the field, it's like, yeah, this is, there are other studies that have done this, or people have done something very similar. Not a surprise. It's sort of in wide circulation. Another possibility is nobody believes that. So, and I would say that those two reactions account for the lion's share when scientists are being frank, because it is by nature an adversarial, not at a personal level, usually not at a personal level. Although if you read a story that I put in the Globe and Mail yesterday, did anyone see that fossil story? That's very personal. Two groups of paleontologists who really do not like each other. So I encourage you to read that story. It's very interesting. But usually science is adversarial, not in a personal way, but it's meant to be, ideas are meant to be tested and challenged. So usually these two responses account for most reactions when people are being honest, like this is something everybody knows, or this is something that no one believes. And then once in a blue moon, someone will respond with a, like they're even trying to, they're thinking about it. And actually that's the kind of response I'm looking for, because it means that a paper has entered the arena, or a study or a finding that others in the field are grappling with. And if it holds up, if it's replicated, or if there is supporting evidence, then there's a sense that perhaps the field will actually have to respond in some way and maybe change thinking about some particular thing. So alien life on planet K2-18b, that's nobody believes that. But what I want to talk about now is more like in category number 3, where it's just sort of like, like there's something here. And that is interesting, because that often makes for less interesting headlines and less spectacular coverage. But that's where you can actually see science kind of changing before our eyes. And for me, I find that especially exciting and interesting as people are grappling with data and trying to process what they didn't expect. And it's kind of becoming unhitched from particular models or biases that people might have. And we see that happening all the time, but it's kind of interesting when you see it in real time. So, expecting the unexpected. This is what everyone said when James Webb was launched. There would sort of be a canned response when you talk to scientists, what's going to be great? And people, what are you most looking for? You sort of imagine the questions you would ask as a journalist if you're talking to senior research astronomers or younger astronomers who are, looking forward to their projects, looking forward to using data from JWST. They might talk about specific things they want to look at, specific questions they want to answer. But often, and scientists have kind of taught each other, especially with JWST, because there's just so much coverage, they kind of all taught each other how to say, but the thing we're most excited about is the thing we don't expect, right? Everyone says that when there's like a brand new, they don't, people actually are not that keen on something they don't expect, but they say, what we're most looking forward to is things we don't expect. In reality, things that you don't expect can be kind of problematic. But anyway, it is interesting to see how that plays out. But I do agree that genuinely people are looking for something unexpected because it needs, or something that's hard to explain because that is the doorway to a more nuanced or more complete understanding of reality or the universe that we live in. So what's next? I've never given this talk before. I forget what's next. So let's find out. I don't know what to expect. Oh, yes. Yes. Okay. Let's play a game about expectation. Here's a famous painting. Don't tell me what it is. Don't tell me. If you know what this painting is, raise your hand silently. Some people know what it is. But it's okay if you don't. It's not, it's whatever. It's just if it hits your brain the right way, you might recognize this painting. I'm going to give you, so this is very low res. I'm going to increase the resolution and we'll see what happens. Can you recognize the painting now? A few more people. Okay. Be honest, and it's okay if you don't know it, but if you think you know it, raise your hand. Okay, so that was, I improved the resolution in that step by 4 times. So now I'll improve it by 4 more times. Okay? What do you think? Hands up if you know it. We're kind of about half. All right, here it is. Starry Night by Vincent van Gogh. Okay, so I think you can experience, well, okay, so that's fine. You have the idea of how to play this game. Let's try it again. Different painting. Ready? Who recognizes this painting? Okay, no hands. I'm going to improve the resolution 4 times. Who recognizes this painting? Okay, 4 more times. Anyone? Here's the painting. It's called Gaia by the abstract artist Lee Krasner. My daughter, the 14-year-old I mentioned, this is her favorite artist. She would get this on she got it, I don't know if she got it on the first one or the second one. Because of the colors, she immediately picked it out. But you'd have to be a diehard Lee Krasner fan to know it. But it's because there was no expectation here. It wasn't matching with anything that you were bringing to the table. So I think this is a good reminder that sometimes seeing things better doesn't mean that you understand it better. Like you could say, okay, now we're going to have a bigger telescope and see it even better. Okay, now here's a bigger telescope and now we're going to see it even better. But everyone is just as confused. So it's a little bit like this, right? Unless there's an expectation and unless it kind of falls into line with a model or some extrapolation of what we already know, confusion ensues. And actually, kind of in a delightful way, that's sort of what we've been living through the last couple of years with the James Webb Space Telescope, in as much as it applies to distant galaxies in particular. So I've been watching this a little bit. I wish I could know more about it. Of course, you're not talking to an astronomer here, or an astronomer's not talking to you here. I'm a journalist, but from what I have, even just in my reporting, I found this a fascinating. Oh, there's Lee Krasner, by the way. So kudos to Lee Krasner. Okay, let's now talk about galaxies, because I want to kind of connect the dots and talk about how improved resolution that has come with the James Webb Space Telescope did not immediately improve understanding. And why is that? So here, the idea of a galaxy goes way back, and it's had a kind of bumpy ride. Of course, in ancient times, before there were telescopes, the universe sort of, the sky was a kind of 2-dimensional thing. You looked up and there was like little lights on the ceiling, or maybe people imagine little holes poked in a ceiling and there was some kind of firmament or heaven behind. And then we get to the point where the concept of space changes. The 2-dimensional sky becomes a 3-dimensional space. If you imagine the Copernican universe, where the sun is at the center and you have planets going around the sun, suddenly that kind of changes your perspective, and you can, it's not that much of a leap to think about other stars being other suns. Maybe they have planets too. And then you sort of start to think in terms of that three-dimensional universe. By the way, just as an aside, I'm going to give you another quiz. Does anyone know? I mean, we know that Copernicus imagined that the Earth would be orbiting around the sun rather than the other way around. He kind of revived that ancient idea that Aristarchus had among the ancient Greeks. And Galileo supported that idea. But who actually proved and when that the Earth goes around the sun? Any idea? Anyone know the year? Remember, Galileo looked up 1610 with this telescope. Copernicus was like early 1500s, right? Is that right? Or is it early? So what year did we prove? Did science prove that Earth is going around the sun? This might surprise you, 1838. Because only then was measurement of stellar parallax accurate enough that as the Earth is going around the sun, you can see the stars swishing back and forth. I mean, one argument why the Earth doesn't move was that, look, like here's the sky. If this is the sun, when Earth is over here, I should see some stars up above me. And then, 6 months later, when Earth goes around the sun, I see different stars, right? So, but that doesn't happen. It's the same stars all the time. So in ancient, like people were aware that that idea might exist, but the proof, like the counter argument was that the stars aren't moving. But if the stars are really, really, really far away, then the movement is too small to measure until Frederick Bessel could make that measurement of stellar parallax in 1838. So that was really a digression. But the point is, in that case, people had long accepted Copernicus before the actual final measurement came in because it was so consistent with so many other things. Galaxies are different, though. No one really knew what to make of this. Say the universe is full of stars. It seems like a big three-dimensional space, all these stars flying around. There are some issues there with Isaac Newton and, do all these masses eventually converge or not? But, when you look up at the sky, it kind of seems like this infinite space full of stars. Herschel could see that, I've covered up that little square in the bottom corner is covering up the Andromeda galaxy. But you can see, this is, well, it's all perspective, right? I mean, you can cover the Andromeda galaxy with your thumb. Yeah, there it is. So here's a wide angle picture of the northern sky. You can see Cassiopeia up there, and you can see that kind of hazy glow of the Milky Way. And then off in the distance, and then off to the side, you can see this other little patch called Andromeda. Now, even this is a bit deceiving because this is a photograph. So this is already allowing more light to build up than the eye can see. With the eye, the Milky Way is just a fog, and Andromeda, as you've probably all seen on a nice dark night out of town, just looks like a little kind of fuzzball up there off to the side of the Milky Way. So what to make of it? Herschel applied an interesting process where he used his telescope in a systematic way to look at fields across the sky and counted the stars. How many stars are here? How many stars are here? How many stars are here? And just kept adding them up. And you can see if you move your telescope across this field, you can see there are more stars in some places than in others. And it was by doing that he sort of put together this picture. You can see it below his portrait right there, that the universe is some kind of, or the stars kind of form this kind of pancake thing, or this blobby thing that's kind of longer in one axis than another. And he thought of that as the system, and we were somewhere in the middle of it. He kind of put us in the middle because the Milky Way seemed to be all around us. And he wrote about this. Let's see if I can move this forward. Okay, by making the square go away, this now no longer works. So we're we're finding out these hidden connections between things. We're making observations. Okay, there we go. Perfect. So here are a couple pages. Herschel was really on top of it. So we're going back more than 200 years. If you look at the second paragraph in that first page, that page 443, this is right out of his book on the construction of the heavens. It is very probable that the great stratum, he thought of our galaxy as a stratum. He's sort of this big flat thing. The great stratum called the Milky Way is that in which the sun is placed, not where the fun is placed. That's how they wrote in those days. Though perhaps not in the very center of its thickness, we gather this from the appearance of the galaxy. He used the word galaxy. He's using it right there more than 200 years ago, which seems to encompass the whole heavens, for it certainly must do if the sun is within the frame. Okay, so, and then over another treatise, this is like about a year later, enumeration of very compound nebula or Milky Ways, and he uses Milky Ways plural. He's saying, he's pointing out that there are other things, and that let's see, probably much larger than our own system, and being also extended, the inhabitants of likewise may perceive the same phenomena, for which reason they may also be called Milky Ways by way of distinction. So he's saying we're a galaxy, these other things might also be galaxies. That's pretty amazing. However, the idea fell out of favor. I won't go into the long history of this. There are a number of reasons why people didn't buy it. And by the late 1800s, it had flipped the other way. Here's DDO's own Dr. Fernie in a piece written for the Astronomical Society for the Pacific, going through the history of this. And he mentions why. There's a paragraph in that second page. At the opening of the second half of the 19th century, like from 1850 onward, then the island universe theory was at the crest of popularity. And the island universe is this idea that the Milky Way is like an island of stars, and there are other islands out there. Yet by the end of the century, it was once again almost completely discredited. There were at least 5 developments between them that caused the about face. I won't go into all of this history. This is an interesting article if you want to read Dr. Fernie's account of it. But it's a good look at how science kind of seesawed around an interesting topic in a logical way that has to do with what data were available. And part of it had to do with the fact that there were many kinds of nebula visible in the sky. Some of them were clouds of gas, like the Orion Nebula. And those seem to be very convincingly inside our galaxy. So at the time, there wasn't a distinction between, Andromeda, which is a separate galaxy, because the stars couldn't be individually distinguished, and some of these other gas clouds. So all of this, of course, gets cleared up 100 years ago when Edwin Hubble comes along. And I mean, he's not the only one, of course, but the key observation here is a telescope, the 100-inch telescope on Mount Wilson, that can actually distinguish individual stars inside the Andromeda galaxy. And you can see here's one of these famous glass plates that Hubble wrote on. You see where he's got the words VAR, exclamation point. That means a variable. What do you think is significant about that? Anyone? Go ahead. Yeah, it's a Cepheid variable, right? This pulsating star that pulsates at a rate that is related to its absolute magnitude. So it can use those stars to measure the distance to something. And once you had a telescope strong enough to see individual Cepheid variables in Andromeda, you can actually measure the distance. And that was the beginning of the universe as we know it today. That was one of 2 steps that Hubble took to our modern universe. One is that, yes, there are island universes, there are galaxies. The other step is that they're not just sitting out there, they're all moving away from us. Or, well, Andromeda is actually coming right at us, but that's a local thing. Overall, the universe, the galaxies are moving away, and the reason is because space is expanding. It's an expanding universe. And we can see this because, as you see in the bottom right here, the galaxies are redshifted. Their light is Doppler shifted, just like the police would use Doppler radar to find out how fast you're moving. The light is shifted to the red end of the spectrum, which indicates the speed at which something is moving away. And Hubble was, Hubble saw that rule that the farther away something is, the faster it's moving away. And you can then extrapolate and get the expansion rate of the universe. So that was sort of, then we're really looking at the universe as we know it today. And that first emerged about 100 years ago. The interesting thing is, when you're looking at this, you're looking still at something that's kind of contemporary with us. It's almost like say you're on a tall building in Toronto looking out, or Mississauga looking out at other buildings around you, looking with binoculars and looking at people. And you see people that are dressed like you and look like you. And it's sort of, you get a sense that you're looking at your community. That's certainly what you're seeing here. Here's like a 3D map of our part of the universe, up to about 100 million light years. This is local space in extragalactic terms. And it's kind of contemporary with us in time. Of course, as we're looking further away, we're looking back in time. This is another concept that, we've had to kind of wrap our heads around as we've gotten to know the universe better. But light takes time to reach us. You look at the moon, you're looking back in time 1 second, or just over a second. You look at the sun, you're looking back in time just over 8 minutes. You look at Saturn, I think it's a couple of hours, and you kind of go for, and then of course the stars are light years away because it takes years for their light to reach us. But years is nothing compared to the lifetime of a star. And millions of years is nothing compared to the lifetime of a galaxy. So even looking 100 million years across space, we're still kind of more or less looking in our own time. But of course, the implication of this is that if you keep looking, eventually things should start to look different. Because if the universe is expanding, by implication, there was a beginning. Everything was all in one point, or the observable universe anyway. We don't know if the universe is infinite or not, but the observable universe, within the horizon with which light can reach us, that space, running the clock backwards, everything was in one place. And it's been expanding ever since then. So there was a beginning, which is called the Big Bang, whatever that was. And so that means that at some point, if you keep looking far enough away, you're seeing light from more and more remote places as light's been traveling a longer and longer time. You're going to start to see things looking younger. So now you're on the building, the big tall building in Mississauga, looking out. As you look further, instead of people looking like they're dressed like us, they've kind of got Frank Sinatra hats on, and they're talking like this, see? And then you go further, they're wearing hoop skirts, and then it's like the Victorian era, and then eventually it's a completely different time. So that's the idea. Could you start to look further and further back to start to see the beginning of everything, when things started, when the galaxies as we know them were built? Certainly that was not possible with telescopes before space was possible, because you had to really look far and collect this really, really dim and distant light. But now we're getting there. Now, I wish I could have found, when I was at the Science Center, the funny thing about that story that Randy told, 6 months later, I was working at the Science Center. Little did I know this when I was ringing up Tom Bolton to harass him on TV, that 6 months later, I would be working at the Science Center and kind of trying to help program the planetarium there. And at the time, we had a slide that showed kind of the most distant view of the universe. And there were these faint blue galaxies, they were called. There was the scientist who took that, and I was looking everywhere for the picture, because as we all know, the internet sucks now. So you can no longer find things that used to be easy to find. But long before Neil deGrasse Tyson, there was J. Anthony Tyson, and Tony Tyson took this picture of these faint blue galaxies. It was just at the early days of CCDs. I think he was using the Keck, or something on Mauna Kea anyway. And you could see these like little faint blue dots. So these were galaxies that seemed to be blue because they were in the throes of early star formation, way more stars forming than we would see in a galaxy like ours today. And because young stars are very blue, these galaxies kind of had a bluish tinge. Here's the Hubble Space. Once the Hubble Space Telescope was repaired and looking, the Hubble could also see these faint blue galaxies. So you see some of these little, very tiny blue dots. This is a Hubble picture from 1995, of course, named after Edwin Hubble. This is a picture from 1995. And some of those blue galaxies are there, and you can sort of start to see the really little faint blue dots. Now, only a year and a half later, we had the Hubble Deep Field, that really famous kind of paradigm shift where, you know, the Hubble basically spent 10 days. It wasn't 10 solid days of observing, but over a period of 10 days, looked at the same place in the sky where there are no stars, no other galaxies in the foreground. I used to tell people, I remember when I was at Discovery Channel, I worked out how to explain how small that piece of sky was. If you take 2 sticks of uncooked spaghetti and cross them and hold out your hands as far as you can, the intersection point of the 2 sticks of spaghetti is more or less the amount of sky that is covered up by that would cover up the Hubble Deep Field. So nothing there. And of course, over hours and hours and days, this amazing portrait emerged of the deep universe. This was very exciting for astronomers at the time, and it was kind of for the first time opening this window, could we start to see what the early universe was really like. And at the time, everyone marveled at how weird the galaxies looked, and maybe we're starting to see the formation process, like galaxies are being built out of smaller pieces. Nowadays, astronomers are saying, not really. It's just that the galaxies look weird because the Hubble couldn't get all of the light. But it was on the road to doing that. And I'm going to make one more personal reference, which is that year I had my first cover story for Terry Dickinson when I wrote for Sky News. There it is right there, exploring the Hubble Deep Field. Terry was excited to have that story. It was talked about at the, I think there was a JWST meeting in Toronto. Anyway, so if you collect your Sky News, you can go back to the beginning of 1996. But look at the last headline. Fossil life from Mars. Why are we not talking about fossil life from Mars? Because fossil life from Mars was, you know, planet K2-18b of that time. That was the alien life that everyone was talking about, another result that went nowhere. However, Hubble Deep Field, definitely worth talking about. And so now we know that there is this earlier period to look towards, and that was the excitement about James Webb. Could you get there? Finally, with Webb, could you start to see galaxies under construction? There's sort of the timeline. The universe starts in a Big Bang. It's super hot. It's like a glowing sea of plasma, white light, like just hot light, everything white, everything glowing. And then gradually, as the universe expands, it starts to cool until you get to a point where it cools enough that electrons and protons can combine to form hydrogen, which is transparent. I'm oversimplifying this, but by 380,000 years after the Big Bang, light can start to move freely without constantly bumping into ionized particles. And then there's this period where it's totally dark, called the Dark Ages, of course. And you know, what was going on then? I mean, this is a really interesting time. But in the middle of all of it, so as the Dark Ages proceed, after a few 100 million years, which is not a long time, actually, somehow some of these atoms have to start to coalesce, they have to start to group together. Dark matter is playing a role here, shepherding, you know, gravity is shepherding matter together even as the universe is expanding. And eventually you get enough stuff together where stars light up and maybe start to, and also enough matter to form clumps that could become future components of galaxies. And that's the thing, that's called the cosmic dawn in a more kind of colloquial way. And that's the thing that Webb was hoping to find. It's sometimes called reionization, you know, where things start to light up again. And the question here is, time is an important factor. Looking at the clock here, so I'm going to try not to go too far here. Time is a factor because we know when the Big Bang happened. Now, there's a little bit of, you might have heard of the Hubble tension. There's a bit of a debate about exactly the exact moment, but we can look at the timeline of the universe. We know the Big Bang happened. And of course, telescopes are pushing back, pushing back, pushing back. So, you need a certain amount of time to build all those galaxies up. So there is an interesting tension there about, is there going to be enough time to create the universe as we see it? So astronomers were expecting, just like you might be expecting with some of those paintings, to see a point where galaxies are still just taking shape because we've now reached the point where galaxies are being built. Okay, here's the James Webb version of a deep field. This is a little different than the Hubble Deep Field for a few reasons, because it's actually looking at a cluster of galaxies. This is the SMACS 0723 picture. This is the one that Joe Biden unveiled when the first science images from Webb were broadcast to the world. So at the center of this picture is a cluster of galaxies, a lot of mass there, and that's kind of bending the light of some of the objects behind and warping the view. So that's why some of the galaxies look like little arcs. But look at all the galaxies, though. Look how crowded this is. This field is astonishing. Everyone was blown away. Astronomers were super excited because of the density, because there were so many more objects. And it wasn't the big, bright galaxies they were looking at. It was the little tiny ones, because these were things that the Hubble Space Telescope, even at its very best, would not have been able to show. And so just to give you a sense of how much space, look at the bottom center where there's like one bright star there, kind of spiky. I'll just zoom in on that one spot. And, here's a zoom in on that image. Look for the smallest, faintest objects here. You can see none of these are things, those little small dots, these are things that Hubble never would have shown. So now you're looking at really early galaxies. And so this is what astronomers wanted to dive into in 2022, so about 3 years ago, and start to look at these things in detail. So it wasn't long before there were some surprises, because things did not quite appear as expected. There were a lot more of these tiny things than some people imagine there should be, according to models of how the universe forms. And also, some of them seem bigger and brighter. Especially these little, what are they called? Little red dots, LRDs. So like the faintest, little reddest, most distant galaxies, things are like redshift 13, 14, that kind of thing. And so, here are two different fields from the James Webb. You can see little white boxes, and then the blow-ups show these tiny little red galaxies. There were more of those than anticipated, which seemed to suggest galaxies are looking rather large, or large is the wrong word. These would be smaller than the Milky Way, but they're looking rather massive. If you sort of imagine their brightness stands for how many stars they have, which gives you a sense of their mass. So they're looking rather massive and rather abundant for such an early time. And it didn't take very long before the headlines were all over it, right? The James Webb Telescope has broken the universe, or even going a little bit further, like the Big Bang must be wrong. These are impossible galaxies. And, there were some pretty, and of course it was a very exciting time for scientists and astronomers, and they were saying things like, these are impossible galaxies. And there was a lot of hay was made out of this. So if you want, you can relive, as I have relived, like the 2-year saga of the impossible galaxies. But I will just fast forward for you. We're now at a point where it seems like they're probably not so impossible. And the James Webb Telescope has not broken cosmology and has not broken the universe. But it is interesting because it has defied expectations in several ways, and some questions are not answered. But in particular, like you see on the right here, there are lots of these pictures of these little red dots that just seem so abundant and so massive. The answer that started to percolate out last year, about a year ago, is that maybe these dots are more than just about stars. It seems like an obvious answer, but it's not so obvious because well, let me jump forward. Oh yeah, so here's from 2 years ago, and rather than saying James Webb, so to their credit, the James Webb Media Office never said the James Webb Telescope broke the universe. Instead, they just kept pointing out there sure are a lot of galaxies, and they let the astronomers fight it out. But as I said, a year ago, we sort of got a bit of an answer. And this is last year. Maybe the galaxies maybe they're not too big for their britches. So there's a lot of arguing behind this. This seems very benign to, if you're just kind of picking up this press release, but this sort of puts the lid on a lot of back and forth in the research community about whether models can or cannot take into account the galaxies that Webb is seeing. And there were people contending, look, the models just cannot make galaxies this big. There's a fundamental problem here with our understanding of how galaxies form, and Webb has shown us this. And that was very exciting to think, man, maybe something really big, maybe it's going to require some change, like new physics or something, or something we don't know about the age of the universe or something like that. So the answer that came back, sort of, there's been tug of war on this, is another part about the early universe that hadn't really been considered seriously until about a year ago. And that's, a lot of galaxies have supermassive black holes. Now, in our part of the universe, local space, there are galaxies like this. Our galaxy has a supermassive black hole. There are bigger galaxies that have bigger supermassive black holes. I think usually they're about 0.1% of the mass of the whole galaxy, something along those lines. And also, like the really big ones, we know how many there are in more local space, or local space is not the right, I'll say contemporary space. Because of quasars, like because of active galaxies, you can sort of count where are the galaxies. When there's a black hole and it's massive, stuff falls into it, it gives off lots of X-rays, and then there are radio waves as the gas goes flying out the jets and so on. So you can kind of count up how many of the big black holes are around. And that would not be enough to account for what's happening in the early universe. But if you have a different, but if black holes are present and flamboyant in the past in a way that it does not resemble the present, then perhaps that is a way to account for this. And in particular, if black holes are more massive than these early forming, relative to the galaxies they're in, if they make up a larger share of the mass of an early galaxy, then all of the glowing light and stuff falling in, the energy around that supermassive black hole might actually be adding quite a lot to the light that's coming from that dot. And instead of the light being accounted for just by stars, it's stars plus a really honking big black hole, big relative to the galaxy that it's in. And that might make galaxies seem brighter than you would expect, and that might account for this. So that's sort of where we're at now. However, it doesn't explain everything, because these galaxies are still more abundant than models think they should be. So there are things we don't get yet. And I'll point out a few things that we don't get. This is a really early time in the universe, and the universe is much warmer. You've heard about the cosmic microwave background, perhaps. We know that we're bathed with the light of the Big Bang from far off in the distance 13 billion years ago. It's about just under 3 degrees Kelvin. We're talking about a time when the universe is less than 5% its current age. even the cosmic microwave background is a lot warmer. And the universe is overall denser. And the composition of the universe is different. You know, obviously less heavy metals and so on. And star formation is a complicated thing because it's fluid and heat transfer. It's like it's like the hard courses in physics. And, you know, so it's probably the case. It's probably fair to say that these processes are not that well understood in the context of this very different early universe, which is very different from the universe we're living in. And that may sort of account for why expectations are not being met. So I'm just going to finish off with the thing that I really enjoyed covering the most in all of this saga the last year or so, which is the Canadian part of it. So I'll just introduce again this concept of gravitational lensing. This is where you can have a very large mass and you can have an object far away behind that mass, and the light is warped or bent because gravity bends light. That's part of Einstein's theory of general relativity. Space is kind of curved or warped in the fourth dimension, and as light beams, which are following straight lines past that mass, they're kind of redirected. So this warps a picture. But you know, when you think of a glass warping light, imagine like taking like when I was a kid, there used to be these like heavy glass paperweights, and they would sort of be like lenses. You could almost use them like magnifying glasses. But yeah, that's the thing. It's like a magnifying glass. You can magnify a more distant object by looking at how its light. You can see a more distant object by looking how its light is warped by the gravity of something that's closer. So that brings us to this Canadian piece of so Canada has something like 450 hours of dedicated time on the JWST. I think I've got that right. In return for building the fine guidance sensors and also an instrument on that kind of combines with that on the JWST. So Canada has time, and part of the way that Canada has spent its time is with this survey called Canucks, appropriately, which involves looking at massive clusters of galaxies, not at the galaxies in the cluster, but at the galaxies behind that are being magnified. It's like taking the James Webb as this massive telescope, fantastic telescope, and then pointing it at another natural telescope to then look even deeper and to see what galaxies you can see. So here's a story that we did in the Globe and Mail last December, where a group from, these astronomers are all over the place, but they had originally met and started off as postdocs at the Dunlop Institute at U of T. And they've been looking at at galaxies around these massive clusters, and you can see, so they have nicknames for these galaxies, and one of the researchers that does this, Lamia Maula, she's from Bangladesh. She has these kind of fun names. So this one is called the Firefly Sparkle Galaxy, but you can see what's happening here. It's really phenomenal. You're seeing a galaxy that's just really, really far away. It should just be a speck. But because the light is passing by the supercluster, or this supermassive cluster, the light from the galaxy has been spread out and magnified. And what you're seeing is like a string of lights. So in that central oval there, the galaxy is not like an individual piece. It's like spread out into these little specks. And what those specks are like individual clumps that are coalescing to form the galaxy. This looks like it's what the paper was contending when this study came out, and this was published in Nature, is that this is sort of the construction of a galaxy similar in mass, or one day will be similar in mass to our own Milky Way. So not so much like these little red dots, some of which are further away, and maybe the little red dots are really sort of like the 1%. They're little red dots to us, but they're actually like the big massive galaxies of the distant universe. They're like the billionaires. This is more like, these are the average galaxies. And when they form, this is what they look like. And what's interesting is because it's being spread out in this way by the gravitational lensing, you can see These individual clumps, they can, and if you can see them as individual clumps, that means you can measure the light from them individually. And you can look at the light from all those little clumps at different wavelengths. And that's how you find out how old a group of stars are. Because if you take groups of stars of different age and you look at their light through at different wavelengths, you can see the difference in kind of the age of their populations. Like a younger group of stars will look bluer and so on. So they can sort of use that age in separate parts and separate clumps and get a sense of the formation history of this. And there's even some companions around this galaxy that are probably going to coalesce to form it. So this is like a snapshot of it. This is starting to now really be like the cosmic dawn, or getting closer anyway, because you're starting to see fragments coming together to form a galaxy like the Milky Way. And what astounds me about this picture is how much the natural gravitational lens has magnified something that we just have no business being able to see. So this companion galaxy, you see the main galaxy, Firefly Sparkle, and the companion galaxy, the one that's companion number 2, their actual distance apart from each other would be about 1/4 the distance of the sun to the center of the Milky Way. So just think about, how that's being spread over. And I mean, you're still looking at a very tiny, small part of a JWST field, but just imagine that amount of spatial resolution, something 1/4 of the size of our distance from the center of the Milky Way. We're seeing it laid out for us, almost like a dissection. Now, this group is hoping that what they will do is be able to start to see individual globular clusters forming inside early galaxies like this. But it's still not the very beginning of galaxies. So it means that galaxies are forming earlier than expected, more abundant than expected, and that's where I kind of harken back to there are conditions about the early universe that are not well understood yet. Anyway, I encourage you to look at that story if you want to find out more about it. I think I was going to click on something else, but I'm going to stop here. There are some amazing, amazing images of these galaxy fields, and they're not the really super dramatic pictures because it's not like a planetary nebula or Jupiter or something like that. You're just looking at little dots. But if you kind of glide over or zoom into these really deep fields from James Webb, it really is kind of a feast for the eyes. And it's just amazing to think how far we have come in just this short time. And no wonder everyone's confused. And it might be 20 years from now when we'll finally know what these dots are telling us. And for sure, we will not be talking about aliens on K2-18b, I don't think. Anyway, thanks very much.
All right. If you have a question, please put your hand up. Speak nice and loud. And I'll repeat the question. Are we zooming this? All right. So I'll repeat the question. Any questions for our speaker?
I'm just going to say, I'll remind everyone, not the astronomer, but I will do my best.
What'd you say, Ivan?
Not the astronomer.
Oh, not the astronomer. Okay.
Is it?
Yeah.
This is not as far as those little red dots. I think it's like redshift 8 something. So it's like, so we're saying like maybe 600, like this is very approximate. Maybe it's like 600 million years after the Big Bang. Whereas some of those really early things are more like 300 million years or roughly after the Big Bang. And of course, once you get really far back, it also depends on which cosmological model you're going with. But anyway, this is like, I'd say roughly 600 million years after the Big Bang.
Dragonfly.
No, dragonfly. Different thing, yes. There's only so many flies. Yes, that's right. Yeah.
Yeah, Bob Abraham's project.
Fantastic story. Absolutely fantastic story. And Bob's quoted in this piece as well, just as a sort of as an observer of this. But yeah. And then there's also a dragonfly that's flying to Titan, but that's a whole other story. So. Oh, got it. The question was whether there was a connection between Bob Abraham's dragonfly but this is Firefly, so it's 2 different things. But there's a connection because Bob's in the story. Go ahead.
Try to repeat the question.
Right.
If you
So
can.
the question there is, what information can be gleaned from these lensed galaxies? So you're correct that they're not looking at individual stars here, but they are looking at clumps of material that are sort of, if you look at a photograph of a nearby galaxy, especially like I don't know, like a 1950s era photograph, and things kind of look clumpy in the spiral arms. We might be looking at things on that kind of scale. So large associations and star-forming regions, perhaps. But maybe they're forming as individual pieces that are kind of either they're forming together or they're coalescing together. I mean, obviously there's dark matter in the picture that's helping draw things together. That's now the limit of what I can tell you because people are working on this to try to figure out what it says. What they're really trying to do is match this to models. Like when you put all of this, when you put all this mass and heat and energy into a model and crunch the numbers with gravity and so on, can you reproduce something that looks like this? And if not, what are we missing? So that's sort of where we're at. People are trying to explain, people are sort of looking at the models that exist and trying to see, can they explain what we see? And if they can't, what does that mean in terms of what's being left out or what is not being understood? And I think one thing that people are coming around to is star formation was somewhat different at that time. But I don't know what that means any further than that. So, and Bob Abraham might say something different at this point, but also this is something that's like changing every few weeks. So you have to really keep on top of it, which I have not been. So anyway. Oh, that's a really good question. I mean, the next, so there are a few things going on, right? We're about to, and at the moment, there's a lot of it. Sorry, I'll just repeat the question. The question has to do with, what's the next telescope, what's coming after James Webb. So I'll answer in a few different directions. In the space telescope arena, of course, there's the Nancy Grace Roman, which is the one that was called WFIRST a long time ago. And that's a much wider field mirror. That was a bit of an opportunity. This thing's been around for a while, but the whole point was it was built to be to be part of a spy telescope looking down at Earth, and they had one left over, so you can have a space anyway, whatever. But the wider field, someone correct me if I'm wrong. I think the idea is then you could make use of that for things like dark energy, dark matter, kind of like larger scale distribution. Also, this is the kind of thing that the Vera Rubin telescope is going to be doing. It's approaching first light down in South America and in Chile, where it can kind of look at the whole sky at once. So there's going to be a period of time where we're going to be hearing a lot about the big picture. And to some extent, Euclid is doing that. Euclid is this fantastic telescope, space telescope that Europe launched. It has a much wider field than the JWST. It's not going this deep. I think where we're going to start to see beyond Webb, before there's another Webb, is some of these giant telescopes on Earth, like the EELT. Of course, there's still this question, will the 30-meter telescope ever get built on Mauna Kea? Canada has a share of the 30-meter telescope. In a way, James Webb was supposed to sort of be picking targets for some of these bigger ground-based telescopes, and we've just been talking about how what electronics can now do in terms of turning a ground-based telescope almost effectively into a space telescope. And so with these giant mirrors that are too big to be in space, I think that's probably going to be the next step. But I'm sure people are thinking about what comes after Webb in space, but I don't know where that conversation is at. So the question is, how do we solve the problem of people understanding what's going on, in particular, how science works? Because science is a bit of a paradox, right? It's wrong a lot of the time. And it's like stumbling in the dark when you're on the edge of knowledge. But in the aggregate, gradually, information emerges that's extremely useful. And no one knows exactly where the good information is, right? So it's this random search. I mean, people do try to direct it. They try to optimize resources, but often the big discoveries come in unexpected places, often in cross-disciplinary places. Like, who knew that if you were studying why yogurt goes bad, it's going to turn into like a new way of editing the genome, that sort of thing. And like Nobel Prizes come from things like that. COVID is another good example. It was hard for people to grapple with how can we know so much about this and yet not know what to do? And you sort of start to realize it's just a reminder that science is this big, fancy vehicle that can take you all over the place, but it needs fuel. And the fuel is data. And if there's no data, it's just this fancy vehicle parked on the side of the road that no one can drive. So the early days of COVID, there were so many examples like that. And people were just guessing, kind of like intelligent guessing, but based on SARS or based on other experience, like experts were extrapolating from what they knew, just like when we were looking at the pictures and trying to guess what the pictures were. And then as more data appear, it's like, oh, this is different from SARS, or this is this, this is this. And you start to get a fuller picture. And there's still a lot of things we don't understand. So I think that these are the three things I would most want people to try to know. Like if someone said, how do we have an education program for the public? I don't know how to do it, but here are three things I would want to have covered. Let's see if I can remember what they are. The first one is to help people understand what's plausible. So, when you're presented with, oh, science has told us this, or here's something on the internet, here's something in social media, what is plausible? And you sort of need you do need a basic frame of reference for how the world works, or what science more or less tells us to understand. Is this a plausible extrapolation of what we know? So you have that, at least that first, like, does this make sense or not? The second is, what's the evidence? To get people to ask more directly, okay, you're telling me this, how do we know that exactly? And what are the, and which then takes you to what are the possible problems with that? Now, it's tricky, right? Because there are a lot of public education programs about things like vaccines or climate change where people feel like they're not allowed to question. Like people might say, well, we're not allowed to question climate change because we're just told we're supposed to, whatever. Not exactly. There is evidence, but, people should be able to understand and interrogate the evidence. I think that is actually really important. The third thing is the thing I mentioned earlier, and I think this is really hard for people to grapple with, which is uncertainty. That uncertainty is built in, it's a feature, it's not a bug, and there's just stuff that we don't know. So whatever you're being told about a scientific result, it's provisional until more evidence comes along, and we just have to keep living with that fact. And you're right, people complain and they get angry, especially if lives are at stake. And in my own reporting experience, the most poignant and direct example of that was, I'm sure there are people in this room, like me, who your first vaccine during COVID was the AstraZeneca vaccine. And then a period of time came where maybe don't take that one. And for some people, that seemed like a huge failure of public health and of science and of authorities. It was actually science doing its job in the right way. Communication wasn't very good, but it was like, oh yeah, we told you this last week. Now there's new data. It's starting to emerge. And of course, people were fighting about the data for a month, but now the fight is kind of inching this way. Like, actually, maybe don't take this one. Because there's a risk factor we didn't see earlier. That's science doing its job. But it was not interpreted that way, and it was often not presented that way in the media as well. But that's where the uncertainty comes in, like, we don't know. And the problem is sometimes when you're trying to create a message, and I don't want to, I think it was not easy, like for the people who are in public health trying to, facing this incredible unprecedented health crisis. I don't want to minimize how hard that was. And you're told, you got to make the message as simple and direct as possible. So the message became, take the first vaccine you're offered. But that became a stumbling block when things had to pivot. So so what I'm saying is that's tricky. But I think somehow the concept of uncertainty has to still be part of how people understand science, and yet accept that, you know, it's imperfect, but it's such a powerful tool. We have to keep doing it. It's more subscriptions to the Globe and Mail would definitely be a step in the right direction. My wonderful partner, my wife of many years, is a teacher, and you know, she gets a front row seat to how under-resourced our education system is, and I think that Ontario is not the only province or only jurisdiction where that's the case. So we do need to think about how to invest in the future. And I have to say, leaving the job of providing information to AI is probably not the right way to go. And so I'm worried about that. So I don't have a good answer. Well, so what I'm telling you is that what we're seeing happen now is not the answer. But we're going to have to try to figure out how to, yeah. Yeah, and trust is a big part of this too. I was on a panel last week actually with Eileen de Villa, who was the Toronto Public Health head of Toronto Public Health during COVID. And yes, before you can, you have to be able to have a trustworthy relationship and conversation before you can even talk about the thing that you're trying to communicate. And so everyone found that out. So I guess the answer is it's not going to be easy. Yeah. Maybe we have to reconstruct how we have to reconstruct everything about how we think about how we exchange information. So, okay, there's some really good questions there. So for the people who are listening at home, there was a very long complimentary section. That was very nice to hear, but I'm not going to go into details about that. Thank you very much. Then there's this interesting question about planetary defense, and this example not too long ago where there was an asteroid that was shown to possibly be on a collision course with Earth. That's really an overstatement, but you know that its future trajectory might possibly include flying into Earth, and then later was found, no, that's not a problem. Why not worry more about that sort of thing than worry about things like alien life? So I would say from a strictly news point of view, both are big stories, or both can be stories. Also, both can be totally overhyped. It's way more interesting to talk about an asteroid about to hit the Earth than to talk about climate change, even though climate change is the ever-present existential threat that's way more important to talk about. With respect to planetary defense, you know, people did ask me at that time, you know, like, what about this asteroid? And, you know, for those who follow the way this works, this is a perfect example of where understanding uncertainty matters. It's a little bit like the hurricane that's coming to your, you know, is this hurricane going to hit our coastline? Is it going to hit our city? You know, there's this massive zone of uncertainty. And when, you know, there's a report that an asteroid might be on a collision course with Earth, what it's really saying is that there's a larger than 0% chance, but that could be a very tiny percent. And of course, it's based on very few observations. So then you need more data, and as you have more data, then you refine the trajectory of the object, and it's like a tube in space. Here are all the possible places it can go. It's like a tube that's kind of going through these keyholes that might determine where it goes from there. And then as you get more data, that tube shrinks smaller and smaller, and eventually Earth is excluded. And so far, every time, that's what's happened. And of course, you're always interested, like, you know, but the bottom line is that's likely what's going to happen. Still, it's important. Now, is it more important than whether or not we find life out there in the universe? They're sort of related in a way, right? We want to preserve ourselves, presumably. So that's why we care about planetary defense. Well, why do we want to preserve ourselves? Clearly, so we can brag about what we've done when we find other life, right? Like when other life turns up and we can, you know, there's an interest in, you know, are we alone? And is there anyone else like us? Can we exchange recipes? Can we, it's curiosity. It's impossible. It's one of the fundamental questions we have. So both are important in different ways. That's what I would say.
One last question.
Oh, you don't want to be the last question. Okay.
Who hasn't asked? Who hasn't?
Yeah.
Last question.
Oh, like of these two things. Yeah. Yeah. So companion number 2, and I'm now reciting what Lamia Mala said to me. So approximately companion number 2, its distance from the main part of that firefly would be on the order of tens of thousands of light. Yeah, so like about a quarter of our distance to the. But you're seeing that distance smeared out over a much larger area because the light beams have been warped and spread out by the gravitational lens. So we would, if it weren't for the gravitational lens, we would never be able to see that kind of detail.
But that invites the question. We are talking about the spatial resolution dimensional state, hundreds of light years.
Yeah.
That's true.
No, tens of thousands.
Tens of thousands.
Yeah.
Okay. Fine.
So we're not yet at sort of like individual star systems or anything like
Well,
that.
it would be individual star forming.
Yeah.
This is what
Right.
we are talking.
Okay. But that's still incredibly remarkable. Yeah. I mean, and of course, all of that is still reduced to a tiny little speck when you put it in the context of it. Yeah. Well, I think, one thought I want to leave you with is that there's this very real effort to look for things on the scale of globular clusters, which to me is astonishing to think about that. But that would only be with the help of these lensed galaxies. Anyway, there we go. Thank you very much.
Thank you.